So, I just wanted to ask if there was any clarification or queries from yesterday. So, we can spend some time on that, because there were only few who were asking questions. So, I am not very sure if everybody got what I was trying to say. So, in ZAC OTFS you have these carrier waveforms, right? So, there are m into n of them, right? I mean, each point here basically is a different carrier waveform corresponding to a different value of delay and Doppler shift, right? This one over here 0 0, that is basically your standard pulse train, right? And if you shift it by, if you give it a Doppler shift of, so suppose I want to generate this carrier, right? What will I do? I will start with this carrier, I will give it a Doppler shift of 2 times 1 over t, right? So, that gives me this carrier, right? And then on this carrier I will give it a delay shift of 1 over b, and then I will get this carrier, right? That is how all these other carriers are generated from this carrier at 0 0, right? That is the basic idea, right? Now, suppose the response of the channel to all of these carriers is not the same. That is just like in OFDM, or if you send sinusoids of different frequencies, they will experience different gains, right? I mean, the subcarrier gains in OFDM, for example, is different on different subcarriers. Similarly, here also the response will be different. Not only different, if you, I mean, in case of LTI channels, when you transmit a sinusoid, you receive the sinusoid of the same frequency. But here it is not like that. If you, let us say you transmit this standard pulson at 0 0, and suppose that the channel had, there was only a single path in the channel, and that had a Doppler shift of 3 over t and a delay of 2 over b. Then even though you transmit at 0 0, what you will actually receive is, you will receive this pulson, isn't it? So, it is not like OFDM where you transmit signal on a carrier and you receive signal on the same carrier. There is a spreading, right? There is a delayed Doppler spreading, right? And that is why when I was discussing equalization, you have to equalize all of them together. Now, on the same channel, if I transmit some other pulson, let us say this, then what I will receive is something else, and what I receive will not be the same as what I receive when I transmit 0 0. So, that is what I mean when I say that the response of the channel to different carrier waveforms is different. So, let us say I transmit this standard pulse train 0 0, and I observe the response of the channel at the receiver, right? And I record that, I store that, okay? Is it possible that from that response, if you know that response, is it possible that you can guess, you can make an accurate guess of what the channel response will be if all of these other carriers are transmitted? If you can do that, then it is a predictable modulation. That is the meaning of predictability, that based on the response of one carrier, based on the channel response to one carrier, you are able to predict or guess or make a good estimate of the response of the same channel to the other carriers. So, when a modulation is predictable, right, then your pilot overhead is nothing. You just use one carrier for pilot and that is enough, right. But when you have a doubly spread channel where you have both delay and Doppler spread, right, and you are using sinusoids to communicate, then the sinusoids don't form a predictable modulation, because if you send information on a sinusoid of one frequency, it will give you some response, right. From that response you cannot guess what the response of the channel will be if you send other sinusoids of other frequencies. That is the problem with OFDM, and also with time domain pulses, right. Whereas if you use pulse on, then you know that the output is simply given by the twisted convolution of in the discrete DD domain. The output that you observe in the discrete DD domain is equal to the twisted convolution of H effective with what you transmitted. So, if you know H effective accurately, you can guess, you can predict what the output is going to be, right. And I described yesterday a way of estimating H effective, wherein you just send this standard pulse on at 0 0. Okay. Well, I discussed, if I am not wrong, this one here, right. I said you just transmit at, so you can transmit at any place inside this box. Okay. And as long as that crystallization condition is getting satisfied, this is your pulse on at Kp comma Lp. Okay. I mean Kp divided by B and Lp divided by capital T, which I have shown with a red dot here, right. Now, when you transmit this over this channel doubly spread, what you are going to receive will be a twisted convolution of your pilot with H effective. And when you do the math here, you will get, basically you get a summation over n and m, right. But you can actually separate one of the terms which corresponds to nm00, because that is going to be in your own box. Okay. I mean this term. Okay. And the other terms are basically the same term, but shifted along delay and Doppler by shifted by integer multiples of capital M along the delay and by integer multiples of capital N along Doppler, right. I have just shown one box, actually this. So, that first term is basically this pink ellipse, but you will also get ellipses everywhere, if you just go to the right or left by integer multiples of tau p, they will just repeat quasi periodically. But I do not care about them, because I know that everything repeats. So, it is enough to just observe what I am receiving in this box. And so, from this pink ellipse will basically give you this term, right. And the spread along the delay of this term depends on the how much is the delay spread of your channel, right. And similarly, the vertical spread along Doppler is the spread along the Doppler, right. And therefore, if these red dots are separated by, the red dots are separated by the delay period. In the discrete domain, the delay period is capital M, right. So, if this spread of H effective is less than M along delay and it is less than N along Doppler, then all these terms will not overlap with each other. Even inside this summation we have so many terms, even they will not overlap with each other. And because they do not overlap, you can actually kind of, if you observe only in this region here, you will only see this one ellipse. And that from that you can actually estimate your H effective, because that is what I showed here, right. Because this is your pink ellipse corresponding to n comma m equal to 0 0 for k comma L belonging to the support of H effective. So, this set H is all k comma L pairs for which H effective has significant values. Okay. And outside that you just put your estimate to 0. Inside that you can actually compute using this equation. If you replace this k with k plus kp, you will get k here. Similarly, if you put L plus LP, you will get L here. Of course, you have to put L plus LP here also, and then you take this term to the left side and you end up with this equation. In a frame, so this what I have shown here is basically one frame. So, this is in the discrete Doppler domain, right. This is your pilot, and then you will be sending data on the other ones. Okay. So, once you are able to estimate this, then it is easy, because remember, when you look at the matrix vector formulation, right, there was a mistake here also. This should be H effective instead of DD, this should be H EFF. Okay. See, if you want to do the equalization, you should know this H effective, right. Only then you can do equalization, because this matrix depends on H effective, and so that is how you estimate H effective, by sending a pilot somewhere in your frame. I do not know if that answers your query. Okay.
Can you go back to the slide 72?
Yeah.
Yeah, you just mentioned that the beauty of the OTFS, OTFS is that you can just estimate the basic channel seen by the basic awesome. Then you can kind of interpolate or predict other channels. Okay.
Yeah.
So my question is that it seems that you can have this property because of you transmit signal only within the small kind of coherent regions, which is defined by the maximum delay spread and also the maximum Doppler frequency you can that you can apply. So that in this kind of the small coherent regions.
Yeah, so this is like the coherent region in the delay-Doppler domain. Yeah, because so I mean those quasi-periodic copies should not overlap. Basically that, right?
But I think in your lecture yesterday you mentioned that all the information are contained in this box, right?
Yes.
Everything else are simply
it's just a copy, replica.
Okay.
Yeah.
But in the wireless communication, okay, that we just have a limited baseband frequency to transmit. So if besides the useful information contained in this box, where you have the kind of a spectrum replica everywhere, then how can you, or kind of when you transmit a signal, how can you kind of confine that the signal only located within the desired the band, the frequency band.
Right.
Another one is that if you want to achieve more information within this small box, then you have to tile the box into the smaller.
So you have to increase your B and T.
Okay.
Because
so is there any limitation? I mean, nowadays we are pursuing for larger and larger baseband frequencies, maybe up to 1 gigahertz. Okay, so can you kind of implement a long enough delay spread or a large enough Doppler frequencies so that you can fully make use of the available baseband?
Yeah, see, I mean, one frame need not cover the entire 1 gigahertz. You can have multiple frames, right? So you could have one user which is only using 10 megahertz. So for him, capital B is going to be 10 megahertz, and the signal at just before his power amplifier, he needs to upconvert. So he'll upconvert his signal to the right portion of that 1 gigahertz complete band. And another user will be allocated some other region, he'll upconvert to some other region. So that is how it will work, right? But for each user will not get 1 gigahertz, right? Maybe 10 megahertz or so.
Okay.
And even for each user, if they want, they can split into bandwidth parts or something like that. So, and coming to the first question, I think it's a very nice question, that in the delay-Doppler domain, the signal is everywhere, right, from minus infinity to plus infinity, because it's just copies. Then how come it has finite time duration and finite bandwidth? Is that the question? Yeah. It's very simple. I'll try to explain that using that standard pulse on at 0, 0. Okay. So when you start with the standard pulse on at 0, 0, it's basically just a pulse train, right? And the pulse train is from minus infinity to plus infinity, right, in time, right? And the pulses are separated by tau p seconds, right? That's this one. Yeah, this one, right? So that's the standard pulse-on Dirac delta, not the physical pulse-on. Obviously, this is, I mean, if you take the Fourier transform, that also is like a pulse train in frequency, and neither of them is, I mean, in time also it is from minus infinity to plus infinity. In frequency also, it's everywhere, right? Now, how do I make this into a waveform which is time limited and bandwidth limited? So the way, I mean, the simple way of doing that is you take this, okay, and you convolve it with a sinc filter of bandwidth b. Now when you do that convolution, what will happen is each of these Dirac deltas will then become like a finite duration pulse. I mean Dirac delta doesn't, I mean Dirac delta is a Dirac delta, right? But when you filter it, it will become something more like what I have drawn here, right? And the width of these, each pulse will be roughly 1 over b. And when you take the Fourier transform of that, in the frequency domain you will see that you will only see these pulses between minus b by 2 to plus b by 2, and outside that you will not see any pulse. I mean that's your normal Fourier theory. But in the time it will still be from minus infinity to plus infinity. And then the next step is that after you do the filtering with sinc, you then just multiply it with a time window which is there from minus t by 2 to plus t by 2. The effect of all this, see the delay-Doppler domain as such doesn't exist in this physical world. What exists in the physical world is just time domain representations, right? Even the frequency thing that we think of is in our mind, right? It's in math, it's on paper, right? I mean the waveform that we really transmit is always a time domain representation of all these other representations, right? Isn't it? So just like I gave you this example, right, you could have a signal which has finite bandwidth but infinite time, or you are also otherwise you could have a signal which has finite time and infinite bandwidth, right? Now in this case, because I want to have a finite time as well as finite bandwidth, what I will do is I will filter this with a sinc pulse and multiply with a time window, right? And when I do that, what will happen is, so the effect of that is that earlier you were having a Dirac delta here, right? I mean this is again the mathematical delay-Doppler domain. But when you do this filtering with the sinc, this Dirac delta will actually spread over 1 over b. And when you do a time windowing over t seconds, the same pulse will then spread over 1 over t along the Doppler. And that is all very mathematical. I mean this is the only physical insight. And when you take the Zach transform of that, you will see this physical pulse-on which in the time domain is limited to minus t by 2 to plus t by 2. and in the frequency it is limited to minus b by 2 to plus b by 2. So, it will be time and frequency limited, but mathematically in the delay-Doppler domain it will be just repeating everywhere. So, it's just like I mean in signal and systems we teach students about periodic signals which exist from minus infinity to plus infinity. We teach them Fourier series. In reality such a signal never exists, right, but we still teach, right, because there is reason for the underlying math, there is importance, right, because from that we derive the Fourier transform. Of course, I cannot give an exact analogy of this thing, because I mean I understand that even if you limit the signal in time and bandwidth, the delay-Doppler representation will still be quasi-periodic and it will still be everywhere. Okay. But I mean you have to just think of it as math, it is just a mathematical construct. It has to be thought of like that. It does not directly translate to reality unless you take the inverse Zach transform and then you go to the time domain. But when you go to the time domain, you will see that it is time and bandwidth limited. So, and that is what matters to us, right. But it was a good question. I know, I mean this is one sticky point, because generally we are used to time and bandwidth limited signals, right. And now here we have a representation which is not limited. I mean it is everywhere along delay and it is also everywhere along Doppler, and that can be confusing sometimes, but that is how it is.
Question?
Yeah, please.
So for OFDM, the time domain signal is simply a sum of weighted complex sinusoidal.
Yes,
right?
yes.
And similarly for OTFS, the time domain signal is a weighted Poisson.
Yes, yes.
But for OFDM, to generate the implementation is done through IFFT and
Yes,
FFT.
yes, that is what I will teach today.
Okay, so meaning the OTFS.
Yeah, it also can be done in a similar way.
Okay.
But I thought maybe yesterday was a first day with lot of new things, so I think people do have questions, right, and I got some interesting questions. But I think that is a good thing. I need to also think of maybe some example to make it easier for people to understand. Why is it that in the delay-Doppler domain your signal is everywhere, but in time and bandwidth it is limited, right. See, you have to remember one thing, you could be limited in time and bandwidth, but in the delay-Doppler domain, I mean the way it is defined, the Zach transform, the way it is defined, that is what makes it quasi-periodic, I mean the way it has been defined, and I think there is a reason for it to be defined like that, because you have to somehow avoid that getting stuck into the Heisenberg's uncertainty principle, right, which says that a pulse cannot be localized simultaneously in time and frequency. So that is why I have to create infinitely so many pulses, so that it is not really localized, we have infinitely so many pulses, but then within a certain time window there is only one pulse. So that is why I have to generate a train of pulses, something maybe like on those lines maybe. But very nice question, thank you. Yeah, please. Yeah, please. Thank you.
I always wondering what is the key for OTFS to outperform MC-OTFS when creating high voltage?
That's a very good question. See, in OFDM, okay, as long as there is no inter-carrier interference, everything is fine. The problem happens when you have Doppler, and that Doppler is significant compared to the subcarrier spacing, right? If the subcarrier spacing is much larger than the Doppler spread, there is no problem, right? OFDM is good. But when you have significant Doppler, then you have interference between carriers, right? And if you ignore that interference and assume it to be noise, then obviously your performance will get hit, because the SINR, the signal to interference and noise ratio, will degrade, even though your signal to noise ratio is okay, but the signal to interference and noise ratio will degrade because of the interference. What is the solution to that in OFDM? I mean, right now what they do is they increase the subcarrier spacing, but when they do that, the symbol duration will shrink, but the cyclic prefix size is still the same, and so your overhead of the cyclic prefix increases. If you don't want to do that, then probably the only solution is that you do a joint equalization of all the subcarriers. So, just like what I am doing here in OTFS, right? In OTFS, all the subcarriers interfere with each other, right? So over here, see, I mean, this is the channel delay-Doppler spread, and it is more than the spacing 1 by B and 1 by T. The spacing along delay and is 1 by B, along Doppler it is 1 by T. But the spread of the channel is more than that. So, the carriers in case of OTFS, they interfere with each other, and that is why I have to do this matrix formulation, y equal to hx, and that is a big matrix, right? Suppose the number of carriers you have 1000, then this matrix will be 1000 by 1000. You can do something similar in OFDM. You have 1000 carriers, 1000 different subcarriers, and each one of them is creating interference for the other, right? So, you can also write some model like that for OFDM also. But then you will need to know the channel coefficients. Now, the channel coefficients in case of OFDM will be these interference. So, each subcarrier is interfering the other subcarriers, right? So, there is a complex number, right? So, that channel is difficult to learn in OFDM, because that is a 1000 by 1000 channel. So, there are so many coefficients, right? How do you estimate it? Okay, even if you use all the subcarriers as pilot, you cannot still estimate 1000 into 1000 coefficients, because you will only have 1000 equations. If you see y equal to hx and the dimension is 1000, then you have 1000 equations, but the number of unknowns is 1000 times 1000, definitely more than 1000, right? So, there is no way you can estimate these what is the interference, the coefficient from one carrier to the other, right? If I transmit a 1 on a particular carrier, what is the complex number received on the other carriers? It is very difficult to estimate. You may say that, okay, I will do it slowly, in one symbol I will estimate this, and then so in the next symbol I will estimate another set of coefficients. You can do some, I mean, basically what you can do is, in the first symbol you transmit a 1 on the first subcarrier, and then you transmit 0 on the other subcarriers. So, what you will receive is a vector which is basically the interference caused by the first subcarrier to all the other subcarrier. But then you have to repeat the same for all other subcarriers also. So, you will need 1000 symbols, and then you are probably assuming that during those 1000 symbols your channel is not changing in time, which is not true, because you have Doppler. So, there is no way with OFDM framework, there is no way you can estimate this big H matrix, whereas in OTFS you can do that. You just need to know H effective, that is all. That matrix all the entries of that matrix depend only on H effective. So, you just in the same frame you had the pilot in the middle and the rest was data. Using the pilot you estimate the H effective, and then you make this big matrix H using the estimate of H effective, and you do your joint equalization of all the carriers. But you can't do that in OFDM. So, the philosophy basically is that OFDM is kind of OFDM works by preventing intercarrier interference. I mean intercarrier along the frequency, and inter-symbol interference it is preventing by using cyclic prefix. So, the philosophy in OFDM is to prevent ISI, and in that process its overhead increases, right. The philosophy in ZAAC OTFS is completely different. You embrace ISI, you let ISI be there, but then you equalize for it. So, that is the difference. This result here. Yeah, exactly. Yeah, you are right. So, this what basically it is showing is that if you have Dopplers around 500 hertz, it is not a problem. I mean MC-OTFS is as good as ZAAC OTFS, and the reason is because it's basically predictability. Yeah, so it's almost as predictable, because remember MC-OTFS is also sending kind of something like pulsons, right. The only difference is that they don't have quasi periodicity. They have exact periodicity along delay and Doppler. So, that is the difference. And when your Doppler is 0, it does not matter, but when the Doppler is non-zero, then it matters. That is a good question. Why? I think it has to do with this thing. Okay, this was the MC-OTFS input-output relation, right. So, I think it is basically that, I mean your convolution and your twisted convolution will probably become the same if you have low Dopplers, something like that. Something like that is probably happening. Okay. I mean when you have low Dopplers, then the channel is almost like an LTI channel, because there is very low Doppler, right. And when you have an LTI channel, then it is fine. I mean then your twist, whether you do a twisted or a linear convolution, they're probably the same. So, I think that's the reason. And I wanted to also do one clarification. When I was discussing the history of OTFS was invented by Ronnie Hadani. The first paper on, I mean I showed you these two papers of mine, right, in 2021. So, the novelty of these papers was that these were the first papers where the receiver was based on ZAAC transform. The transmitter was still MC-OTFS. So, it was like a mix, something between MC-OTFS and the full ZAAC OTFS. And then later on we had this paper on ZAAC OTFS, where you have ZAAC OTFS both at the transmitter and at the receiver. So, this is the complete thing. This thing is something like in between, okay, because the transmitter is still MC-OTFS, although the receiver was based on the ZAAC transform. Okay, so as Professor Kelvin said, so today I will try to focus on how would you really implement this. For example, as Professor Kelvin said, when we implement OFDM, we never do a continuous Fourier transform, right. It is always a discrete Fourier transform, FFTs, right. So, there has to be something equivalent in this case also. So, that is the focus of mostly the first part of today before lunch. Now, in this figure here, what you see in the chain at the bottom right here, this one is basically your xdd is your, that's your discrete delay Doppler signal, right? And from that you create this signal. I mean, this is where your information symbols are, right? So you take your information symbols and you quasi periodically repeat them along delay and Doppler, right? And that's how you get this signal, right? The information symbols are finite, m into n, right? But this signal, for this signal, k and l are going from minus infinity to plus infinity because of that quasi periodic repetition. And you take this and then you mount it onto Dirac deltas, right? So the k comma lth is put on a Dirac delta which is at k by b along delay, and the location along Doppler is l by t. And you have this signal xdd tau nu, right? And then we do this pulse shaping, if you remember, and then we just take the inverse Zach transform, you get your xt. But this, you cannot implement this, right? Because this is all continuous. This is all continuous delay Doppler. I mean, how will you implement this? You can't even do it in MATLAB because this is continuous, right? So the processing, signal processing chain on the top is basically telling you how you can do it using MATLAB, basically using discrete signal processing. So the way to do that is you take your delay Doppler, discrete delay Doppler signal, and you apply this transform. It's called the inverse discrete Zach transform. And what it does is it gives you the discrete time realization of your discrete delay Doppler signal. Okay? For example, your inverse DFT, inverse discrete Fourier transform, what does it do? It takes the frequency realization, the discrete frequencies, and it converts into your discrete time signal. And then you also have DFT. DFT takes a discrete time signal and gives you the discrete frequency, realization of the discrete time signal, right? It's just like that. It's very similar to that. There's no difference at all. And so this IDZT is given by this equation. It's a very simple formula. So the nth sample of the discrete time realization, you just have to add the delay Doppler signal. You replace the delay index by n, and you simply add along the Doppler indices from L equal to 0 to n minus 1, because after that it repeats. In the Doppler domain, your period is capital N, right? The scaling factor is just to make sure that these are unitary transformations which conserve inner products and energies. What I will also show in the next slide is that xn is periodic with period mn. So this signal that it gives, I mean, this is quasi-periodic and this will be periodic. It's a periodic discrete time signal, right? Even in case of OFDM, right, if you really look at the math, then your IDFT always gives you a discrete time signal which is periodic. You can test that, you know that, right? So this is very similar, right? And then you take, so xn is not limited in time. It is n, small n is going from minus infinity to plus infinity. And you take that and you put it onto Dirac deltas in continuous time. So the nth symbol or nth sample is put on a Dirac delta at the time instance n over capital B. So 1 over capital B is like, the sample duration basically. Now this signal that you got is going to be continuous time, right? But neither is it limited in time, nor is it limited in bandwidth. It's not limited in time because this small n is going from minus infinity to plus infinity. It is not limited in bandwidth because the delta signal has infinite bandwidth. Is it okay? I just wanted to, I forgot your name. Kevin, yeah, sorry, yeah, Kelvin and Kevin, right.
And we get the frequency is
So what is the Fourier transform of delta t? It's 1 everywhere. So yeah, so there's no, the bandwidth is not limited, right? Right? That's why. Okay? And then, so this is your continuous time signal, this one, which I am calling as x tilde t. Okay? So x tilde is basically this guy. So how do you limit in bandwidth? First you do a filtering with something like a sink. So this one is going to limit it in that bandwidth minus b by 2 to plus b by 2, and then you multiply with a time window. But now the question that is probably going in your mind is, how is this equivalent to this? So basically for a given xdd, both the chains should produce the same xt. Only then they are equivalent, right? I will prove that. It's complicated. It's actually all of this is, if you want to really, so basically if you go to the OTFS book, in chapter 8 there is this appendix A, which has the full detail and proof of all these things. Alternatively, if you do not have so much time, you can also go to this archive paper, just recently put on archive, and this also has, you know, these things, I mean the proof of all these statements that I am making in more detail.
Doesn't have exponential term like
It doesn't have?
Doesn't have a exponential term like DFT.
Yeah, because it's not going from frequency to time, right? It's from the delay-Doppler domain to time. Okay?
Maybe because it is quasi-periodic.
Yeah, yeah. The DD domain signal is quasi-periodic, yes, yes.
So here you generate your ZAC OTFS signal from the time domain perspective. I was wondering if I apply the IDFT to convert the DD domain signal into frequency domain, and in the end of this chain, you have the IFFT to convert into the time domain signal.
I have done that in that.
Compatible to OFDM system.
Yeah, so I did that. That's this paper. That is this paper, and that's why we are. This was a big paper which I always wanted to write, because with this paper now we can go to the standards, and so this is called ZAC OTFS over OFDM. So I am showing that this IDZT can be written as a composition of these two blocks. That is what you said. Right? It's basically that thing. Okay, so I'll come to that also, and then you can implement your ZAC OTFS as a small precoding. You go from delay-Doppler to frequency, and then you give it to the OFDM modulator that is already in the existing hardware, and so your ZAC OTFS can be implemented just as a simple precoding in software over the existing, you know, in the existing modem.
And in this case, we don't need CP, or we still need CP.
No, obviously, I mean the CP will be there, because the modulator, the CP OFDM, they will always put a CP anyways.
But
Yeah.
it is not necessary.
It is not necessary for us, but if I have to be compatible, then they will put it, right? I can't help that, right? I think you should start working on ZAC OTFS. It is high time, right? I mean, I'll show the equivalence, okay? Once I show the equivalence, it's obvious that if the IDZT was something else, then this XT and this XT will not match. So it has to be this. So let me go to the proof now. Of course, I mean this part I'll not prove, because this is what we did yesterday, right? I mean, I showed that when you do this kind of pulse shaping, it is equivalent to doing a twisted convolution, you know, basically filtering in the delay domain, in the delay-Doppler domain with this thing. I mean, these two are equivalent. Either you do these two, or you just do this in the delay-Doppler domain. Let me show where I showed that. You remember this figure? So that is what I am using actually. I mean, if you have I mean, this is not just for this signal, you know, this is something very general. you have any time domain signal, if you do this filtering followed by windowing in time domain, you can alternatively do the same thing in delay-Doppler. You first go to the delay-Doppler representation of this signal, which is this thing, and then you just do a twisted convolution with this filter, with this delay-Doppler filter, which is obviously related to, you see the same W1 and W2. Of course, this W2 is the Fourier transform of this capital W2. And after filtering whatever you get, you go back to time, you will exactly get this thing. So, this is the equivalence that I am trying to use now. Because this equivalence is very general, it is not just restricted to these pulsons. It is true for any time domain signal. Okay? You have any time domain signal here, this equivalence between doing this and doing this is valid. So, I will go back now. I can show that, because the only thing now I need to show is that this signal is the delay-Doppler representation of this signal, right, because I need that. If I need to show that this part and this is equivalent, that assumes that the input here and there are basically the same signal. I mean, this is the time realization, this is the delay-Doppler realization. So, that is the only part that I need to prove now, right. And that is not very difficult. Let me go to the next slide. So, in this slide I am trying to show that the delay-Doppler representation of x tilde is basically this signal. Okay? But that is the same as showing that if I take the inverse Zag transform of this signal, I should get x tilde t. I mean, they are equivalent statements, right, because Zag transform and inverse Zag, I mean, if I compose them, you get the identity, right. So, that is what I will show. I'll start with the inverse time Zag transform of x dd tau comma nu, this signal, and that is given, I mean, this is the regular usual function, I mean, this is your inverse Zag transform, right. And now here for this x dd, I will replace with this double summation. Of course, I have to replace the tau with a t. Okay. So, when I do that, in this integral the double summation comes out, x dd kl comes out, because remember this summation is, this integral is only over the Doppler axis, and that too from only 0 to nu p over one period. Okay. So, even now the first term is also not depending on nu, it is only depending on t. So, that also comes out. What remains is in the integral is only this part. Now, nu p over capital N is the same as 1 over t, because capital N is t times nu p. Okay. So, this is the same as L over capital T, and now I do this integration. Okay. Now, assuming that, I mean, of course, there is a if you see here this L, where is it? So, the L is actually going from minus infinity to plus infinity, and you have this Dirac delta at L times nu p over capital N, right. But the integral is only between 0 to nu p. So, the question is, what are the values of L here for which this integral is not 0? Now, you have to think of this delta, imagine the delta function. Where is the delta function located? At L times nu p by capital N, or you can also say nu p times L over capital N. Now, if this L is equal to n plus 1, then Kevin, where is this Dirac delta located? If L equal to capital N plus, even if it is capital N nu p, right, which is just at the border. What if what if the small l is equal to capital N plus 1? Then the location of the Dirac delta is outside outside this range of the integral, right. So, L equal to capital N, L equal to capital N plus 1, capital N plus 2, for all of them the integral will give you, Kevin, 0. Similarly, if L is equal to -1, then also the Dirac delta is located at nu p times -1 by n, which is, and that location is not in this range from 0 to nu p, right. So, therefore, this summation over small l will give you 0, I mean the terms in this summation where L is either negative or L is greater than equal to capital N. The corresponding integrals for those values of L which are either negative or they are either greater than equal to N is 0, because the Dirac delta in those cases is not located within the time window 0, within the Doppler window 0 to nu p. So, therefore, this summation now becomes a finite summation from L equal to 0 to n minus 1. Is that okay, Kevin? And for each value of L equal to 0 to n minus 1, what is the value of this integral? Now, the cases where you have small l going from 0 to n minus 1, for any such value of L, this Dirac delta is located inside the, inside that this 0 to nu p interval. And if you integrate a Dirac delta, what do you get? You get 1, exactly. So, for all those terms in this summation, this integral is 1, and that is how you go from this line to this line. Is it okay so far? Not okay? Okay? Okay. Not sure why? No, I mean, which is the step which is confusing you? This one is fine. Okay, okay. So then you get this step, right? And but what is this? I mean, if you look at this part here, isn't this related to this? Looks similar, right? It's exactly equal to square root of n times xk. I mean, I have put a k here, okay, because this summation is over k, okay. I got to put a, if I replace this k with a n, you will exactly get the same expression, but it does not matter, k and n are variables, right. And therefore, if when you replace this with square root of n times xk, you will exactly get this expression, because n times tau p in the square root is exactly equal to t. So, that is how you get the square root of t, and then this remaining thing you can see, because this summation is xk. So, it becomes summation over k xk times delta t minus k by b, which is basically this summation, right. Okay. So, this shows that these two signals are basically, the time and the delay-Doppler realizations of the same signal. Okay. And then we showed that this is anyways equivalent, and therefore, this xt and this xt is same. So, that is good feedback. Maybe for the next courses, I will put in more of these short proofs. I think that helps to increase the depth of understanding, right. Okay. So this is how you will actually implement Zach OTFS using any digital or discrete time, discrete kind of signal processing. Okay. I just put a slide on IDZT. Okay. But there are a lot of properties of IDZT which I have not put here. If you go to the textbook in chapter 8 appendix A, there are a lot of other results also. Okay. But this one I have just restricted to what we need to know. So, first of all, IDZT for a quasi-periodic delay-Doppler signal, it will give you the discrete time realization of that signal, okay, and it is given by this equation. IDZT is only defined for quasi-periodic, okay. Again, I am sorry about this d, it should be in the subscript here, okay. I mean xdd should satisfy this relation, okay. It should be quasi-periodic. This is the equation which basically means that xdd is quasi-periodic. If xdd is not quasi-periodic, you cannot have its discrete time realization, it is not possible. Can you show that also one more thing. Next I will show that when you take the inverse discrete Zag transform of x dd, the signal, the discrete time signal that you get is periodic with period m into n, and that is not very difficult. I mean, if you take this equation, you replace this n with n plus mn, then you have to replace this with n plus mn, right. So, you get this equation, right. But as I will just show now, even when you have a quasi periodic signal, which is quasi periodic in delay with period m and exactly periodic in Doppler with period capital N, such a quasi periodic signal is exactly periodic in delay and Doppler with period mn, and this is what I have shown here. For any integer p and q, if you shift the delay and Doppler indices k and l by integer multiples of mn, then if you see this formula, you replace, what you do is you replace this small n, you replace the small n with p times capital N, replace this small m with q times capital M, and use this result, right. What do you get? You will get this expression, right. I mean, this small n will be replaced with p times n, so you will get this term, and for this one you will get, I mean, that one remains the same. But what is this? This is 1. So, this shows that a signal that is quasi periodic along delay with period m and along Doppler with period capital N is actually exactly periodic along both delay and Doppler with period capital M into capital N, Mn, right. And therefore, by that result, this should be exactly equal to this, because this is n plus mn, right. So, if you replace this with this, that basically is your IDFT. There is another typo, there should be a square root here, there should be a square root here, okay, it is a typo, but that is same as xn, right, right Kevin. So, that shows that this x of n is actually a periodic discrete time sequence with period capital M into capital N. Now, we come to the receiver. See, at the transmitter we showed that you can implement with discrete signal processing using that IDZT, right. Now, what I have in this figure in the bottom here is what we have discussed so far, right. This is your Zag OTFS receiver, the way we discussed it yesterday. So, you take the Zag transform of the input signal, you go to the delay Doppler domain, and then you do the matched filtering, right, in the delay Doppler domain, and then the output of the matched filter is you sample that. That is how you get the received discrete delay Doppler signal YDDKL. But the problem with this is that this Zag transform is a continuous delay Doppler Zag transform. How do you implement that in real life? You can't implement that in real life, right. So, on the top chain is an implementation which is based on discrete processing, okay, namely discrete Zag transform, okay. And I mean, it is very easy because, I mean, this part here, the first part is obviously equivalent to this, right. This is the same as what we, I mean this is also filtering, right. So, this followed by this you can replace with a single twisted convolution with this filter, where W3 is this one, small w4 is the Fourier transform of capital W4. This is again the same template that we used at the transmitter and that we also discussed yesterday. I just did a recap of that just now. Is that okay, Kevin? Sorry?
W2
window. Yeah, the capital W2 is a time window. Yeah.
What is the
Small.
W3?
No, I mean that is also, I mean I have just kept it general. To keep it general, I have just said that it is a filter. I mean this is because see, along with this received signal you will also have noise. So, this filter will just noise and interference from other things. So, this filter will just select minus b by 2 to plus b by 2 in frequency. So, this could be your sink of Bt for example. So, it will just take the signal in your band, okay. And then this is your usual time window, right.
So-called HQ.
Yeah, I mean it is not exactly matched to your transmitter filter, I am still calling it, but I mean for it to be matched there is a particular, I mean this, if it has to be matched then you cannot choose W3 and W4 freely. They have to be depend, I mean this WRX will basically depend on what is WTX. So, that I did not cover. Can I use the board here? Okay. So, matched filter. So, WRX tau nu, okay. If you really want to implement the matched filter at the receiver, then it has to be WTX conjugate minus tau minus nu times e to the j 2 pi nu tau. If you want to do the matched, so matched filtering basically means applying a filter which gives you the best signal to noise ratio, right, the maximum possible. So, when you do the math, you will see that this is the receive filter that will maximize your receive signal to noise ratio. But what I am using is something different because I want to connect it with the CP OFDM modulator, that is why. And yeah, I mean this result is very similar to our time domain, right. See, at the time domain at the transmitter, if you use the pulse PT, right, for pulse shaping, then at the receiver the match filter is what? It is conjugate P of minus T, it is something like that, right, something similar to that, okay. But you are right, if you really want to do a match filter, it cannot be just anything, it has to be related to WTX, okay. In fact, in the book I have derived why WRX should be of this form. It is like a 1 or 2 page proof inside the second chapter in the appendices of the second chapter. So, now this first part is equivalent to, I mean if you are doing a two-state convolution with this filter, then you can do the same thing in time like this, and so therefore this YDD and this YT are basically the same signals, okay. I mean that is from the template that we had, right. So, this YT and YDD are, YT is the time realization, YDD is the delay-Doppler realization of the same signal, okay. That is why I have shown these arrows. That is because this signal is the same for both of them, the same RT is going here and the same RT is here. Now, what I just want to show to you is that after YT, what we discussed yesterday was simply you sample this signal on that information lattice, right. So, when you sample at tau equal to k by b, n equal to L by t, you get YDD KL, right. And I will show that that is equivalent to doing these three things. First, you sample this continuous time signal YT into a discrete time signal y tilde, which is basically this equation. It is called sampling. I mean this everybody knows, right, but your sampling rate is equal to the bandwidth, okay. After that, you have to do this periodization. Basically, you take this y tilde remember is not a periodic signal. It need not be a periodic because this y of t, I mean this received signal is a time limited signal. So, is not it, Kevin? Because what the transmitter, it did a windowing, remember. So, the transmit signal is time limited, therefore, the received signal is also time limited, and therefore, this YT anyways you are multiplying with a time window anyways here, right. So, the YT is time limited, right, and when you take the discrete time samples, they are also limited in time, is not it. And therefore, this y tilde n, because it is limited in time, it cannot be periodic, right. But my YDD KL, which is the delay-Doppler signal, the discrete delay-Doppler signal, has to be the time representation of that the discrete time representation has to be a periodic discrete time signal, whereas this is not periodic. So, I have to convert this to something that is periodic with period mn, and that is why I have to do this periodization, and this is how I do it. Now this y tilde was not periodic, but I take y tilde and I shift it by integer multiples of capital Mn, m into n. So, I have multiple copies of y tilde with these different shifts which are integer multiples. These are shifts in the discrete time. So, now I have copies of y tilde with different shifts and I just add all of them together, okay. Then that is this signal basically yn, and obviously by design yn has to be periodic with period mn. So, now I got a yn which is periodic with period capital M times capital N, and I can do the opposite of what I did at the transmitter. At the transmitter I did IDZT, right, which took your xdd to xn. Now I will do the opposite. I have a periodic signal yn, I will take its discrete Zag transform, which is going to give me this signal's discrete delay-Doppler representation ydd. But I have to show that this sampling and all these three are equivalent, which means that this output here and this output here is exactly same. I have to show that, right? Otherwise then there is no point, right, if they are not equal, right. So, here I have just given the formula for dzt. So, this is yn. So, if you know, your input is yn and you do this kind of processing and you get yddkl, okay. Now, Kevin, at the receiver I have to implement this in your digital signal processor, right, but I should do this calculation for what values of k and l. This mathematical definition is defining yddkl for k going from minus infinity to plus infinity, L going from minus infinity to plus infinity. But in your receiver, do you really want to, you can't calculate all those, right. So, what do you do at your receiver? Exactly, from k equal to 0 to m minus 1, L equal to 0 to n minus 1, and the reason is because the discrete Zag transform of any periodic signal, any mn periodic signal is always quasi periodic with period m along the delay and period capital N along Doppler. That is a mathematical result, okay. So, therefore, this yddkl is quasi periodic, it is repeating with m and n. So, there is no need to calculate yddkl for all infinitely many k's and l's, right. Is that okay? So, I will come to the proof later, but I just wanted to give you some, where is it? Here, this is the proof. So, I need to show that these three blocks do exactly same as the sampling operation, right. This is going to be a little involved, okay. Let me try my best to prove it. I just included it for the fun of it, so that we have some depth also. Now, this was your periodic repetition, Kevin, right. Is there anybody else apart from Kevin who can volunteer, who can help me in proving this? Any other student? Your friends, Kevin? Okay, not ready? No, okay, it is okay. So, let us start with the sampling operation, okay. So, what is ydd tau nu? Ydd tau nu is the Zag transform of yt, right. You have yt, you take the Zag transform, you go to ydd tau nu, right. But yesterday we saw that the Zag transform of yt is given by this basic this is the transform, right. And then you how do you get yddkl in the bottom chain? You take ydd tau nu, which is this expression, and you replace tau with k over capital B, that is the sampling on the information lattice, and you replace nu with L by T, right. That is how we defined the receiver yesterday, right. Now, when you take this expression and you replace tau with k by b and nu with L by t, you get this expression, right. It is very simple. You take this tau, instead of the tau I put k by b, instead of this nu I have put L over t, right. Also this L into tau p over capital T will become equal to n times L over capital N. Why? Because this capital T is equal to capital N times tau p. So, the tau p will get cancelled, only capital N will remain here. So, it will become n times small l by capital N, right. So, let us remember that. Okay. I mean, you see this L by capital N here, right. Further, this summation over n is from minus infinity to plus infinity, but I will write this small n in a different way. Okay. I will write it as in this form. So, I will replace the summation variable n with two summation variables, one is q, the other is p. Okay. P is going from minus infinity to plus infinity, but the q is only between 0 to n minus 1, because the way I define q, q is defined to be small n modulo capital N. So, that is why q can take values only between 0 to n minus 1. So, I replace this big summation over small n with this summation where q is going from 0 to n minus 1 and my p is going everywhere from minus infinity to plus infinity. It is just a mathematical trick, okay? Nothing more than that. And I replace this n with this thing. So, I get k by b plus, you replace this n over here with q plus pn, okay. But you have this k by b, when you take this b as a common denominator, this b will get multiplied with the tau p in this next term, but b times tau p is equal to, Kevin, m, yes, capital M. And that is why you see that for these two terms capital M is getting multiplied, okay, right. So, this whole thing is equal to this, okay, where I have used this fact. You take this b in the numerator here, because I want the b to be a common denominator for both these terms. So, k you will get from here, but this other term will be n into b into tau p, b into tau p is capital M. So, it will become small n into capital M, and then you multiply this with, this is your n. So, you multiply with capital M, you get these two terms, right. And here you have to replace, here you have to also replace this n with q plus p times capital N, right. Okay. So, that is how you end up with this equation. Is it okay so far, Kevin? Okay. And then what I do is I take this summation over p to be the inner summation. Also, there is one more thing I am doing here. I mean, this is, when I put a round brace, it basically refers to the continuous signal yt. I mean, even here this is the continuous time signal yt at t equal to this value, right. But this time instance is like an integer in the numerator multiplied with 1 over b. So, that has to be some sample, because remember we were sampling at b hertz. So, this is exactly equal to y tilde. I mean, you look at the definition of y tilde. Y tilde is just obtained from yt by sampling at rate 1 by t, 1 by b. That is the sampling period. So, y of this is basically y tilde of the same thing, right, Kevin? Is that okay, y tilde? You obtain y tilde by sampling y like this, yt. So, whatever is here is here. So, that is why this thing is nothing but this basically this expression is nothing but this thing, right. And then you move the summation over p inside, okay, and you put the brackets here. Everything else is outside. Well, outside you only get this term, okay, because you know there are two terms here inside the bracket, but the other one is becoming 1. Why? Because it is an integer multiple of capital N, and then divide by capital N, you will get a e to the j 2 pi into some integer which is 1. So only this q will matter. Now what did you get inside once you move the summation over p inside? What is this? I mean, this is like doing a periodization, right? I mean, this equation is very similar to this thing, see? I mean, this one equation is similar to this one, except that you have to replace n, small n with k plus qm, okay? So this thing inside the bracket is actually y of k plus qm, okay? Remember, y is the output of the periodization block, okay? Is that okay? Huh.
y equal to sigma y delta n plus p.
Which one? Y of? This one. This is the definition. So y of n is defined like this. It is defined. It's a definition.
Because y delta is a limit.
Y tilde is limited. Yeah. But by doing this, I get this yn, which now is not limited. It's actually, this yn is actually periodic with period m times n, and I need to do that because the dzt is only defined for periodic sequence. Only periodic discrete time sequences can give you a quasi-periodic delay-Doppler signal, right? That's why I had to do this periodization. And therefore you once, I mean, so basically this thing inside the bracket is basically this periodized signal at n equal to, so this is your n at n equal to k plus qm, right? And this comes here, right? But it turns out that this is exactly this is actually the equation for dzt. This is exactly the equation for dzt. If you go back here, this was the equation for dzt, right? You exactly end up with the same equation. And this shows that, so what I have done basically is I have assumed this processing. I mean, I have shown that this sampling operation basically gives you this ydd, right? That is what I have shown. Because I sampled ydd tau nu over here, I got something and I showed that that is exactly equal to this guy. Because look at these operations. I mean, first of all, this is your dzt, but this dzt is on this y sequence, y signal which is periodic, and the y of this is basically this only, right? Y of, think of k plus qm as some time instance. So that is equal to this, and so this y can be obtained from y tilde only through periodization. There is nothing else, right? I mean, this is coming into into your equation automatically. I don't have to do anything, right? If this ydd kl has to be equal to this one, then this has to be the output of the periodization block. I mean, obviously this is periodized. Is it clear or confusing? Some facts about dzt, and I think I could be boring you with a lot of proofs here, but this is the last one, okay? And probably I will leave it, I mean, I will not maybe go into detail of this proof, but the basic thing is that if you have a periodic signal with some period capital P, a periodic discrete time signal, then the dzt of this discrete time signal will give you the corresponding discrete delay-Doppler representation, right? Which I write it like this. But I mean, if you are just given a periodic signal with some period, how do you choose your capital M and N? I mean, why? I mean, if I give you just any periodic signal, discrete time periodic signal, but I didn't tell you what to do with M and N, right? Of course, the M and N should be the same M and N which are used at the transmitter, right? Otherwise, it will not work. But when you design a system, you have freedom of choosing M and N. I mean, the only constraint is that the product of M and N should be B times T. I mean, your actually choice of M and N really depends on the delay and Doppler period tau p and nu p. and tau p and nu p you choose in such a way that you satisfy the crystallization condition. So, this is how it is decided, okay, how the m and n are decided. I mean, this is proving that if you start with a y n which is periodic with period m n, and if you take the dzt, then the dzt will give you a discrete delay-Doppler signal which is quasi-periodic with period m along delay and period capital N along Doppler. So, this is the proof that this YDD is actually quasi-periodic, because we need to prove that, right. You want me to go over the proof, Kevin? Or will it become too boring for the class? What should we do, Professor Kelvin? We should see the proof? Okay, good, very nice. Because I did not get any feedback about. Okay. So, now I will prove that I will start with this sequence or signal y, which is a discrete time signal and it has period m into n. Okay. And YDDKL is a discrete delay-Doppler signal which is given and it is related to your y through this equation. To prove that YDD is quasi-periodic, I will examine the value of YDD at k plus nm and L plus m into m times capital N. Because if I show that this is equal to this quantity, then I am done. That is what I have to show, right. So, now you take this expression of YDDKL, which is this one, and you replace k with k plus nm. You replace your L over here with L plus small m times capital N. So, you get this expression basically. I mean, because you replace k with nm, you will basically get, instead of k here, you will get k plus nm. That is why you get, and that n into m I am combining with qm. So, that is how I got n plus q here, okay. And here I replace this L with L plus m times capital N, but this q I am actually writing it in this way. The reason is because I want to have n plus q everywhere. I mean, this q I can write it like this, it is just a mathematical trick. And then you go to the next step, write this. Now, with this one you will split into a term which contains n plus q and the other term is containing n. Now, what happens to, I mean, here you might probably argue that instead of this L I should have had L plus m times capital N, right, also there also, right. But why did why have I just put L there? Because this other thing is an integer multiple of capital N, and so it will just become e to the j 2 pi into some integer which is always 1, right. So, that is why, that is the simplification. And then going to the next step. In the next step, if you see here, the right hand side has, of course, this term, see this one, e to the j 2 pi n L by capital N, that does not depend on q, right. I mean, the summation index is q, it is independent of that. So, what I am doing is I am taking this outside, see, it comes outside. What remains is only this and this term, those are the only ones remaining, okay. And then I do a substitution of variable, because the dependence on q is only through n plus q. So, I define a new summation variable q prime which is defined to be n plus q. So, when q goes from 0 to n minus 1, my q prime will go from small n to small n plus capital N minus 1, that is this summation. And I can replace this n plus q with q prime, right, similarly here also. Now, I am using this fact that yn is periodic with period mn. Because it is periodic, this index, if I just compute the modulo mn value, then also they are the same, right, because yn is periodic with period capital Mn, right. So, if I replace k with k mod mn and q prime m with q prime m mod mn, it is one and the same. And here also if you see this signal, if I replace this, because remember there is a division with capital Mn at the in this exponential. So, if I replace this q prime m also with q prime m modulo Mn, then these two terms are still equal, right, Kevin? That's basic math, right? Now, if you see your right hand side, it depends on q prime through this number q prime into m modulo Mn, okay. So, as q prime goes from n to this thing, for each term, for the term corresponding to a particular q prime, you multiply that q prime value with m and you take the modulo Mn value. But my claim is that whether you go from n to n plus capital N minus 1 or you go from 0 to n minus 1, these terms, how many terms are there in this summation? Capital N. Now, those terms will still be here in this summation also, exactly. I mean, first of all, do not go to this step. In this step itself, if I change the summation limits from q prime equal to 0 to capital N minus 1, I will still get the same terms. It is just that the ordering will be different, right, because you see that it depends only on this modulo Mn value, that is why, okay. You can take a small example and write it down and you can check it for yourself, okay. So, in this summation itself I can write that this is from q prime equal to 0 to n minus 1, and then of course, I mean this and this are equal, and similarly this and this are equal, right. That is always true, right. I mean that is how we came from here to here, from here to here, right, and we can always go back. I mean this modulo thing I just wanted to show you, so that I can convince you that this summation can be changed back to 0 to capital N minus 1, because here everything depends only on q prime m modulo Mn. Is that okay? It is a little involved, but I mean the capital N terms in this summation is the same, it does not change, okay. And so you get back this, right. Now, along with 1 over root n, this whole thing is nothing but that is exactly this expression, see. It is just that q prime has to be changed to q. So, this one and this one is exactly the same, and so that I replace with YDDKL, okay. And so, what we have shown is that if you shift along delay and Doppler by integer multiples of capital M and capital N respectively, then you get back the same YDDKL, but with this extra term here, okay. This is quasi periodicity, okay. Kevin, is it fine? Is it okay? I do not know for others. If there is any question, people can ask, I will try my best to answer that before we move further ahead, or we can take a small break, 5 minutes or something.